Now that we understand what gravitational potential energy is and we have derived the general formula for it, we now understand what that formula is. In this class, we will try to reconcile the two equations that we have for gravitational potential energy. So we know that potential energy is equal to minus G capital M small m upon R. So this is the universal formula. This is the most powerful formula. This is correct in all circumstances. This is the one formula that we have. The second formula that we have for gravitational potential energy is, of course, also there, and that is, so the objective of this class is actually twofold. One is to understand why we have this negative sign. So that is the first objective. Why do we have this negative sign here? And the second is, what is the relationship between these two? I mean, why do we have these two formulas at all? Why can't we just have one? I mean, it is just to make our life difficult, is that it? So this formula obviously appears very simple, and you would be asking, why can't we just always use this one? So that is the intention of this class. We will try to explain both of those two things. One is the sign there, and the second is this. So this, let's first get to the sign. So the sign of potential energy, let's just understand that a little bit. So we will again write the formula, right? We can write it as many times as we want, because it is so very important, right? So we will write this formula again right here, and then here you will see that this formula comes from and configuration in which we have two masses m and m, and for the sake of simplicity, let's just assume that this is earth and this is fixed, and this object m, the small one right here, is any object. The small m is any object, for example this remote, which we are pulling away from earth. Okay, so we are just trying to push it as far away from earth as possible. Okay, and the distance between these two objects is r. Okay, so that is where the r comes from, and if that was the case, then the gravitational potential energy would be equal to minus GMm upon r, the distance. Okay, so this is something we understand. Another thing to note here is that it is not r squared, right? So in the case of the force, we have r squared. Okay, so that is one thing to understand. In the case of the force, we would have, but here we only have r. So that the force was there was this inverse square relation, and that is why we had r squared, and here we have just r, and that is something that you should not forget. That mistake should not be made. Now, why the negative sign comes is because this formula, when we came to this formula, when we derived this formula, we made an assumption that we are increasing r, right? As we increase r, one of the things that you could understand is that the gravitational potential energy should increase, right? Because as we move, that is something natural. As I move this remote away from earth, and I am putting in more and more energy into this remote, I'll have to pull it away from earth, right? And so I have to do more work, and that work gets stored in potential energy. So the potential energy should increase as we increase r. That is something to be understood. Now this r, I am increasing, and when I make this r very large as I can possibly make this, when this r becomes equal to infinity, then at that point I am assuming that my potential energy at this point is equal to 0, right? And that is the assumption which has been made in this formula. So with that assumption, what would now happen? As I reduce r, as I come back to earth, the potential energy slowly and gradually gets converted into kinetic energy. So potential energy would actually reduce as I get closer to earth. So the potential energy would actually decrease. So I can say that delta PE, right, or the potential energy, not delta, that's not the change, but actually decrease. And since it's decreasing from 0, it would become negative. And this is the negative sign that we really see here. So very, very simple, right? This is the reason for the negative sign. Now let us understand what is the relationship between these two formulas. Now it is also very, very important, and why I am saying again and again that the first formula, this one, is really powerful, while this is not so much. Okay, but we will see that in a second. Okay, although it might look simpler, but it is not really that powerful. We will see that in just a second. So this is P is equal to mgh, and this formula is only applicable when we are very close to the earth, right? So h is very much less than the radius of the earth, and we'll just see that in a second. So this formula is only applicable when h is much less than the radius of the earth, which I'll denote with capital R. So this is the radius of the earth. Okay, so this is right here, this is the earth and this is the radius. Okay, I've given you sort of the spoiler here, but just let's now understand. So first we start with this formula. So here we have, again we will make a body, okay, our body m, and then our second body m, and it is starting from infinity. At infinity we have this potential energy, we said that was 0. Oh, very nice, no problem there. And then it comes to a point, we call it 1. Okay, this point 1 is at a distance of r1 from the other body. Then it moves a little further. Okay, then it comes to a point 2, and at this distance of point 2 from our second body is actually r2. Okay, so this is the configuration. This is where we will try to understand if this were to happen, then the change in potential energy is what I would try to understand. And we'll just bear with me while we are calculating this change in potential energy, but it will be very instructive. You will see in a second that because of once we calculate this change in potential energy, we can then understand where this mgh actually comes from. We'll see that in a second. But for now, just bear with me. Let's just go through the calculation. And of course, the calculations are not so difficult. What is the change in potential energy? Change in potential energy will be the potential energy at this point R2, so which we can write it as minus G capital M small n upon R2, and of course then the initial potential energy which was at this point R1, so we will write that as well. Okay, so this one we will write it as minus and then minus of G M upon R1. So this was the initial condition. Initially we were at R1, then we went to R2, and I'm interested in the difference of these two potential energies, and that's what I have done here. So this is potential energy at R2, and this is the minus potential energy at R1. Okay, so this is what we have computed, which will give us the difference, and that's what we are interested in. And this becomes, I'll take the GMM out, which is common, and this becomes, sorry, this is not r squared, this 2 should be here, sorry about that. So this becomes minus 1 by r2, and this minus will become plus 1 by r1. Okay, so notice one thing here, that as I go from 1 to 2, this r2 would be smaller. So this r2 would be smaller, which means that this 1 by r2 would actually be larger. So this 1 by r2 would actually be larger, which means that this negative would be larger than positive. So this quantity would come out to be negative. It is very important to understand. This quantity would come out to be negative, which means that delta P would actually come out to be negative. And that is something that we expect, because when we go from 1 to 2, the change in potential energy would actually decrease. It is going closer to the earth. Okay, we are just using this m as an example. We are just calling it earth so that we can understand it's going closer to the earth, so potential energy should decrease and it should change to kinetic energy, and that is what our formula is also saying us. It is telling us the potential energy change is negative, which means that it is decreasing. So all these things, they all fit together very nicely. Okay, now we are one more step away, just one little step away in just coming to this formula. The mgh. Okay, so let's just do it now. We are just one step away. Look at it. Now understand that we have this earth, the radius of the earth, let us just assume that it is r, and then from this radius r I am throwing a body, and I am throwing it sort of, the body is moving. I am not throwing it, but it is moving from this height h. Okay, so this height is h here, and it is going towards the earth. Okay, so it was at a height h, and then it fell down on the earth. So that is what the configuration is. Now we will calculate the change in potential energy in that circumstance, that the body is at height h and then it fell down. and it fell down on the surface of the earth. So this is exactly what we are computing. Of course, I will not throw this down, otherwise we'll have problem here. But the intention is the same, that there is a body at height h and it fell down to the surface of the earth. So in that case, what would be this is exactly same as this, but my R1 in this case, the initial condition is R plus h, and my R2 is of course just R, because it fell down, so it is just lying there at the surface. This is my R2 is just R. It is exactly same as this condition. So R1 and R2. Now I will substitute these values here. Very simple, no, nothing complicated. GMm, and then what I'll do is that I will use minus 1 by R2. So this becomes minus 1 by R plus 1 by R1, which is of course R plus H. So now we are getting somewhere now. So see, this equation, what happens is, I simplify this and then I get GMm, and here I get R plus H minus R, okay, and then in the denominator I will get R into R plus H. This is what will be there in the denominator, okay. And now I simplify this further, okay. But before I do further simplification, so this R and this H would actually cancel. I make a very small assumption, okay. I just make an assumption. I say that this H is actually much less than R. So this is my assumption, that this H is actually much less than R, which is true, right? Because typically the objects that we are dealing in our terrestrial world are not very high. We are not launching rockets typically, right? That will happen. Of course, I really wish that you do launch rockets and you can calculate those physics questions, but normally we don't do that. Right? So our objects, the height, are typically much less than the radius of the earth, and only in that circumstance we can, if we allow that to happen, if we are in this condition that H is much less than R, only in that condition we can approximate this R plus H with simply R. So in that condition, what does my formula become? It becomes, so I will write it right here. This becomes very simply GMm upon R squared. Okay, so this is simply, this has become R into R, which is R squared, and at top we have H. Now this entire thing we know is acceleration due to gravity, so this becomes equal to mgh. So this is how the formula for mgh came into being. So this is my delta P, change in potential energy, okay, when an object is moving, is changing heights very close to the surface of the earth. Only in that case the change in potential energy can be given by mgh. Okay, that is the first thing to note here. The second thing to note here is that when we are using this formula, we are assuming that this is earth, okay, so this is radius r, that the potential energy here is actually equal to 0. So that is the second assumption that we are making. Any height change from this location, so if we increase height, we will increase the potential energy, because we are pulling the object away from earth. So we are giving it energy, we are doing work on it, and that work is being stored as potential energy inside the object, so that potential energy would actually increase. So at that point, at this point, potential energy is equal to 0. At this point, when I take it to height h, I have done some work here, and at this point the potential energy becomes equal to mgh, and of course this holds only if and only if this h is much less than the radius of the earth, which is r. So hopefully all of these things are demystified now. Now we completely have understood what minus GMm upon r means, and how we came from here to here under which simplifying assumptions. So there are two assumptions that we made. One is potential energy is 0 on the surface of the earth. In this formula there are two assumptions. One is the potential energy is 0 on the surface of the earth. Second is the heights to which we are dealing with is very less than the radius of the earth. And under those simplifying assumptions, we can use this equal to PE equal to mgh. And those two are the simplifying assumptions that we are actually making, that potential PE is equal to 0 at h is equal to 0, and The second is H is much less than R. Okay, so hopefully everything is now clear. We have completely understood these concepts. Do subscribe and like this video if it has really helped you. Thank you.